Hello and welcome back. So in today's video, we're going to be taking a simple neural network in PyTorch and we're going to be improving its accuracy step by step. So I know that we have covered GPT models, neural networks, language models a lot. And if you ever trained a model and thought that, why isn't this model performing better, or why isn't this model more accurate than it's supposed to be, then this video is perfect for you. So the plan here is that we're going to be starting with a basic baseline model. We're going to be measuring its accuracy initially, and then in a later step, we will improve it together and check the final result together. So if you guys are ready, let's go ahead and begin. So first, we actually need to understand what this baseline code actually does. So as you can see, first here we imported the PyTorch and Torch Vision. So why we import these libraries is because they will give us the neural network tools and datasets that we can use for the training. Then, as you can see here, we define the device. So this will tell PyTorch whether to use the CPU or GPU for when it's training. Then right after that, we need to load in the dataset. And basically, we use the MNIST dataset. It's called like this, MNIST, spelled out like that. So basically, this dataset that we're using for this example, it contains thousands of handwritten digits from 0 to 9, and they are all marked as 28 by 28 pixels. So we will use this dataset by converting them into tensors so that PyTorch can process these. And next is the model itself. So this is just a simple model that we used. It basically takes an input layer of 784 values, because as you can see here, it's 28 times 28, which is 784. And there's two hidden layers right after that, and one output layer of 10 neurons. So it's one for each digit. Then between the layers, we use something called the ReLU activation. So simply, this is just this activation will help the model learn the nonlinear patterns, and it will be useful for the training. And as you can see here, as we discussed earlier, there's the forward pass that we use. So basically, what the idea of using the forward pass here is that it will first flatten the image, so convert into a vector, then it will pass it through a layer, so it passes through each layer to produce predictions based on it. Then next up, we get the loss function and the optimizer. So we actually need both of these to train the model. So once again, the loss function, it will measure how wrong the predictions are, and the optimizer will update the weights according to how wrong the predictions were. So it will attempt to improve them each time. And basically we use the cross entropy loss, so the average, because this is a classification task. So it should be getting better each time we train the model. And we have used this before, and we'll use it here again. It's the SGD. This is a simple optimizer that we're going to be using for training the model. Then after that, we have the accuracy function. So this is just an additional function that we did to calculate the accuracy and return it so that we can keep track of how well the training is going. So as you can see here, it will switch to evaluation mode. It will run it on the test data that we give, and it will check how many predictions match the true labels. So then after we get this, we will just divide the correct predictions by the total samples to get a percentage accuracy. And this is the main task of the accuracy function. So finally, for the last part, I'm sure we have seen this before, it's the training loop that we use here. And basically what this training loop does, it will run the epoch that we give it each time. So basically the model will get or see each batch of images. It will then make a prediction on whether this image matches the number. Then it will use the loss function to give us a loss. And then use the optimizer to update the weights based on the loss function, right? So it's the basic training loop that we always use. And then at the end of each loop instance, we calculate the accuracy from the function we just did earlier, and this will help us see how well the model is learning. And if you can see up over here, we have defined the epoch as 5, so we just want to keep it simple, and obviously this number can be changed according to however much you want. And then we run the code, and we can see that it has run 5 times. So for the first try, the loss function is 1620 and the test accuracy is 18. Then, as you can see, as it keeps running the loop, the loss function starts decreasing, and eventually by the 5th attempt it gets to 91%. So it just shows that the accuracy sits around the 80 to 90% range, and this is actually not a bad range, but now we can actually improve this range. So in order to improve the model, there are actually a lot of steps to take. So we'll try 5 steps for simplicity. So we'll try adding more layers, changing optimizer, and improving regulation. So it's expected that each change should push the accuracy higher. So let's check it out. So the first thing we can try to do is increasing the capacity of the model, because right now the network is quite small, so it might not have enough parameters to capture the complex patterns in the data. So what we can just do is increase the number of neurons and add one more hidden layer. So all we have to do is go over here to after the define, so we can increase the number for, say, 128, 256, and 128. We just double it. Similarly, we can double this one as well, 128 and 64, and we can even add a third hidden layer. So let's say self dot fc4 equals nn dot linear. Then we can add 64 and 10, for example. Okay. So basically, the main idea is here that if you have more neurons in a network, you can represent more patterns. But of course, the consequence of this is that too many neurons can cause overlifting, and this is the main disadvantage of using this method. So now let's try and run it again. And for the next step, we can change the optimizer that we use. So as I showed earlier, that we use the SGD optimizer. So this is one of the most simple optimizers, but the main issue with it is that it's slow. So you can just easily switch to any other optimizer. For example, Atom. So instead of SGD, you use Atom optimizer. So basically the Atom optimizer adapts to the learning rate for each parameter automatically. Now obviously it will use more resources, however, it is more efficient and helps the model train better. So once we are done showing all the improvements, you should also notice that the training stabilizes faster and accuracy improves much better. And this is the main part of the optimizers, as they can make a huge difference even if the model stays the same. So for the third step, which actually also helps with the first step, it's to adding a dropout. So we want to prevent the overfitting, which was the main issue of the first step we did with increasing the neurons and layers. So basically a model can memorize the training data, and instead of learning the patterns, so to avoid that, we just use the dropout. And what this will do is it will randomly disable the neurons that we use during training, so the network can't just memorize one path and just keep on memorizing. So we need to force the model in some way to start adapting by learning the patterns. So how we can do this is we first need to add the dropout in the model itself. So if we go over to the model we have here, so we just add self dot dropout equals and then dot dropout. You can choose any rate. For this one we'll use 20% by putting 0.2. Then we can modify the forward function we did here. So we will use, say, self dot dropout. Then we put self dot relu inside. So we just add dropout, self dot dropout to the outside of the forward pass we use. So once again, so dropout. And keep repeating this. And for the last part, it's self.relu self.fc3x. So this will slow down the training, but it will help with better generalization. And this is especially useful when the models get bigger. So this is one thing to keep in mind. And another step for improvement is basically just making the model train longer. This is the simplest step because sometimes the models haven't converged everything yet. So all you can do is just increase the loop amount. So you can just increase the epoch here. For example, let's say from 5 to 10, we double the training amount. So to run the training loop, instead of 5 times, it will run it 10 times. And this is actually a very simple fix. So we can see that the accuracy will climb further when you do this, and it's one of the easiest improvements overall. And the final step that I will cover for this video is that it will be the adjusting rate, right? We can just adjust the learning rate. So one thing you need to keep in mind when you're adjusting it is that if you make it too high, the training will start acting unexpectedly. It will just start jumping around all over the place. However, if you start making it too low, it will become slow, right? So the best thing I would recommend is to slightly reduce it to keep it balanced. So if we go over to the optimizer that we have here, so we can just increase, or I mean decrease to from 10% to 5%. So this will slightly give a, how can we say, a slight increase in the accuracy, and it will make it slightly smoother. It will make this training slightly smoother. And overall this will help with the performance as well. So now we can actually run the improvements. Okay, so while the loop is running, let's give a quick recap. So we just started with a simple baseline model. Then we start making improvements step by step. Obviously there are other ways as well, but we covered the most important 5. So we can increase the model capacity, switch optimizers, and adding the dropout, increasing the dropout, or making the model just train longer, have more loops, and change the learning rate. So each step, it will help the model slightly perform better, but if you add them all together, and even if you want to add additional steps, then you will see a noticeable difference in the performance of the model. So as you can see here, we run the training, we print the first 5 again, just for the comparison, and you can see the average is completely different. So for the first one, the loss function is 324 and the test accuracy is 95%. And by the 5th one, the loss function gets as low as 68 and the test accuracy goes up to 97. So this is a significant increase from the 80 to 90 range to 95 and 97 range. So if this video helped you, don't forget to like, subscribe, and I'll see you guys in the next video.